Okay. Yeah. Good evening, everyone. We have last class we have discussed UART protocol, right? So did you understood everyone what is meant by UART and how we are taking the block diagram for transmitter, receiver, and baud rate generator? How to write the program? Have you learn everything? Have any doubts? Hello. Have any doubts in that? No doubts. Have you practiced? Can you tell me what are the blocks we have in yacht? Can you tell me what are the blocks we have in yacht? What is the um what is the frame format of yacht? Can anyone?
Start with database and past and start now.
Okay. What is mean by a protocol?
Set of rules.
Set of rules. Okay. What is the difference between intra protocol and inter protocol? What is the difference between intra protocol and inter protocol?
Within the system is intraman and out of the system is inter.
Okay. Okay. What is the difference between high speed protocol and low speed protocol? What are the different types we have? In high speed and low speed? Anyone?
In high speed, we have Ethernet, USB, and SAS.
Okay.
And in low speed, we have UART and SPI.
Okay. Okay. So what is mean by interface protocols or peripheral protocols or bus protocol? What are different bus protocols we have? All AMBA protocols comes under bus protocol, right? Parallel communication. Bus is nothing but a parallel communication. Okay, we can transmit either 32-bit or 64-bit parallelly. Whereas these I2C or SPI, all these are serial communication protocols. So only bit by bit we can transmit. Okay, so what is meant by baud rate and why we will use baud rate? That's why only I have given 2 days time. On Thursday, we have discussed the project, right? Baud rate is nothing but in place of clock. Okay, in yacht you are not using the clock for synchronization. Okay, for that purpose we are using the baud rate. Okay, and we have seen baud rate calculations and how to generate the clock using baud rate in the code also. Okay, so once again go through that project details. I have shared the specification code, everything with you. Just go through that. Okay, today we'll see a Verilog project, 4-port calculator. Okay, we'll see 4-port calculator. Actually it's a MS project. Okay, in last August or something, we did MS project. So that is a 4-port calculator. It is very big project, actually very complex project. that complex project we minimized very simply for Verilog students. So we'll discuss that thing. Okay, just we'll see what is what are the specifications, how we need to consider the points here, what are the requirements here. Based on that, we'll write the program. Okay. Coming to design specification, it is a 4-port calculator. Okay, that means we have 4 ports like A, B, C, D. 4 ports will be there. Every port will do some certain calculations like addition, subtraction, shift left, shift right, like that. 4 ports will do each port will do 4 calculations. Okay, each port may have 4 outstanding commands at a time. Okay, there will be 4 outstanding commands. The commands consist of addition, subtraction, shift left, shift right. Okay. The operand data accompanies the commands. What is the operand data? Nothing but whatever we are sending to the addition, subtraction, shift left, shift right, that operand data accompanies the commands. Okay. And since there are 4 ports, there can be up to 16 outstanding commands at a time. Right, 4 ports means each port have 4 different operations. 4 into 4, 16 outstanding commands will be there. Okay, each command from a port is sent serially, one at a time, one by one, serially. Okay, but the calculator log may respond out of order. Out of order means one by one means maybe it mislead. Out of order. Okay, depending upon the internal state of the queue. Queue is nothing but one by one serially the transmitter will be happen, right? So that is in the queue. As a result, each command is accompanied by a 2-bit tag. Okay, 2-bit tag is nothing but it is like a condition satisfier which identifies the command when the response is received. Okay, so that is the specification. According to the specification, they have given the pin diagram also. 4 ports we have, right? So request command, data, request 1, request 2, request 3, request 4. These are 4 ports. Okay. Each port have request command, request data, tag signal, and request to command, data, tag, and for port for command, data, tag, for port for command, data, tag. These all inputs. Clock reset also inputs. Okay, what outputs we have? A data output, response, we should get response also, and tag. Okay, so output is a 32-bit size here. 32-bit size. Input is 4-bit size. Okay, input we need to consider here conditions also given how the pin functions will be work. So request X command in. X is nothing but either 1 or 2 or 3 or 4, like that. 0 to 4 bits. Okay, so 0 means no operation, 1 means end add operation, 2 means subtract, 5 here they given 5. Okay. Okay, so 5 shift left operand 1 by operand 2 places. Okay, 6 is shift right operand 1 by operand 2 places. So these are the commands: addition, subtraction, shift left, shift right. Okay, for both the shift commands, only the lower order 5 bits. That means request data. This is X data 27 down to 31. We are using only 27 down to 31. Why? Because now some girl asked in group, right? Why we have to take only 27 to 31? Why we can't take 0 to 31? Why? Because uh, no need to take 32-bit size for addition, subtraction, shift left, shift right. Only 4-bit data enough. Okay, then you may get the question, then why we are taking the output data as 0 to 31 as input size. We can take output size also, right? We cannot take when you are doing the addition operation. Suppose you are doing addition operation 2-bit input size, 2-bit 2 bit size, but output you will declare always as a 4-bit size, because 2 plus 2 you may get 4. Okay, 4 means it's a 3-bit, under 3-bit, right? So that's why anytime input and output size will not equal when we do the addition, subtraction, multiplication, like these shift operations. Okay, output size value will be increased when we do those operations, right? That's why output we have taken as a 32-bit size, input also 32-bit size, but we are taking as a 5-bit. Okay, of operand 2, the shift amount are used. The calci 1 logic ignores bits to 26 of shift operand 2. This allows the operand 1 data to be shifted any amount of 0 to 31 places. There will be 32 places, 0 to 31. So it will be shifted to any value. Okay, so input 1, input data. What is input data? Operand 1 data arrives with a command. Okay, commands are nothing but addition or subtraction or shifting, like that. Operand 2 arrives, operand 2 data, operand 2 arrives data on the following cycle. Okay, next cycle. Next, output response. When we'll get output response, there are 4 conditions, 4 tags as we call. 0 means no response. 1 means successful operation completed at the output side. Uh, 2 means invalid command or overflow we got. Okay. 3 means unused response value. These are the 4 tags we are looking at the output side. Did you understood, everyone? Did you understood, everyone? Have any doubts?
No, ma'am.
Okay. Okay. These are the design strategies and code we implemented like this. Sub modules, 4 modules. That means 4 ports, 4 modules we have taken. Each module will have input, command input, data input, tag input, clock reset output. Okay, outputs, data, response, tag. These are the each module. Okay. So if you understood specification, we'll go to the Verilog program. Did you understood, everyone? Whatever I have shared you the specification, wait, I will open that also. Have any doubts, girls?
No, ma'am.
Okay. Same. There will be 4 ports. Each port has command, data, tag. But here what they have given means okay, here also 2, 5, 6. Okay. The Calci1 logic ignores 0 to 26 bits of operand, shift operand. This allow only 5 bits, last 5 bits, 27 to 31. You need to note that point. Based on this only, you are going to write the program. Okay. Have you tried how can we write the program for these type of operations? There are two operands only by taking these conditions. These will be the ports. How can we write the program? Do you have any suggestions? You know how to write the Verilog program, how to develop the design we already discussed. Can you tell me how can I write the program here for 4 ports? These all ports should do addition, subtraction, shifting operation. Again, this addition, subtraction, shifting, addition, subtraction, shifting, addition, subtraction, shifting. How can we write the program? Think, take time. And these are the possible timing diagram for request, command input, data input, and tag input. These are the outputs. Response 1, data, and tag. At what time we are generating the input and what time we are getting the output. The lightning bolt response represents some number of cycles passing. The data accompanies the successful response signal. And these are functional verification using system Verilog. Okay, tell me how can we write the program? Have any idea? No? Okay, see. This is the design code. First design.sv, we included calici.sv or v. Okay, so coming to this calculator, this is the top module. Okay, if you see the top module, what we have module 1, module 2, module 3, module 4. 4 modules we have. Same, these 4 modules we are connecting each other, same as yacht. Okay, so in module, this is the module inputs outputs. See here, output data 1, out data 2, data 3, data 4, response 1, response 2, response 3, response 4. All inputs and outputs. Tag 1, output tag 2, 3, 4. Next clock, request command input, request 1 data 1, request 1 tag. Like that, request to command, request to data, request to tag. Like that, request 3 command, request 3 data, request 3 tag. Like that, request 4. Okay, reset. All the top level, all the top level signals we got. Right, this is the top level. So outputs declared with the what are the inputs and what are the outputs. This is the port list declaration. Now what we did, submodule, all these connections, 4 connections, 4 modules we have connected here. Submodule S1, C clock, duty connection, reset, request command in and request command data in, all we are connecting like this. Okay, all these things, from where we are getting all these things? Nothing but sub module. We have written the sub module here. Okay, as a multiplexer, if you see a hierarchical multiplexer, how we have written, by writing one multiplexer program, from that multiplexer program we design hierarchically, right? Same here, we are writing the submodule actual functionality. From the submodule actual functionality, we are deriving 4 ports here. Okay, submodule S1, submodule S2, S3, S4. 4 ports we connected like this. Then it will be 4 port functionality. Okay. So submodule, what is the functionality? According to our conditions here, calculator, what is the functionality? These things we need to write. So input, clock, reset, request command input, request data input, tag input, response, tag. If you see, we have written only 1111 inputs. Okay, not 1 2 3 4. 1 2 3 4 we are deriving here from this functionality. Okay, so declared all inputs and outputs, request, these are the internal reg values, and always at the rate of, if you see the program now, always at the rate of passage clock and reset, begin input 1. For the input 1 or the temporary variables, we are sending the data, request data in. Okay, to the input 2 we are sending request data in, both same values after some delay. Okay, now shift, for the shift value what we are sending in of 27 down to 31. Okay, why we are sending 27 down to 31? That value we need to shift, right? So if request command in is equal to all zeros, if you see here, if request command in is equal to all zeros, no operation, right? So here no operation, that means output response getting 0, output data is getting 0, output tag also getting request tag input, whatever input tag is there, output also getting same tag. Okay, next, request command in is equal to 1. As we taken here, request command in is equal to 1 means addition operation of operand 1, operand 2. Operand 1, operand 2 are nothing but input 1, input 2 here. Okay, so if request command in is equal to 1, output is equal to input 1 plus input 2. Okay, if condition, see here condition, I won't tell the condition because why I want to tell all these things, you need to practice, right? So see, after the session I will share the code, go to this command. Okay, if it satisfies here, output response is getting overflow 10. Why here 10 is getting? Try to get that. Okay, and output or else output response equal to 0 1, successful operation. Okay, that means here it is performing the addition operation. Okay, if this addition operation if this condition satisfied means we are getting the overflow, otherwise if this condition satisfied means we are getting the successful operation. Okay, output tag equal to request tag in, same, whatever input tag is there, that we should get to output tag. Okay, next is subtraction. If request command equal to 2, we are performing the subtraction. So this subtraction, try to get this overflow, why we are getting the overflow and how we are getting the successful operation. Okay, next, request command in equal to 101. 101 means 5. 5 we are doing left shift operation. For the input 1 we are doing the shifting operation. Shift is nothing but what here, 21 down to 31 of 2, as the condition here, as the condition here, the lower, for both the shift commands, only the lower order 5 bits 27 down to 31 of operand 2 are used. Okay, the calci 1 logic ignores the 0 to 26 of the shift operand 2, nothing but input 2. Okay, this allows the operand 1 data to be shifted any amount of 0 to 31 places. Okay, that means input 1 will shift any value based on the this input 2. Okay, so output data is equal to in 1 left shift of shift times. Okay, whatever the shift value is there, that many times this input 1 will be shifted. Output response getting 1, tag is getting tag. Okay, like that right shift right. What is the shift right value? 6. Okay, request command in is a 6. So request command in is equal to 6, output data equal to in 1 right shift of shift times. Okay, that shift times value we are taking in the test bench. You know that output response equal to 1, tag equal to request tag. Okay, finally we return the some else condition. Whatever the else condition you want, you can write the else condition. Okay, did you understood? Simply we written very simply. Okay, any doubts? All the conditions satisfied based on the design specification? Outputs 0, no response, 1 successful operation, invalid, unused. Based on the output, we'll check. All the conditions satisfied? Have any doubts? Hello.
Yes, ma'am. Ma'am, but why we have to take 5 and 6 as a input pins, ma'am?
What? 5 and 6 are input. See, as the condition they have given, we are not taking. Just a second. Yeah, we are not taking our own here, right? So here, as per their conditions, we have taken what the condition they have given. Request 1, command 0 down to 3 size. In that 3 size, you can write here. Suppose okay, 5 6, right? In place of 5 6, I am taking 3 4. Request command here, it will generate 2 power 4. In 2 power 4, we can take any value. Suppose if I take 3 4 here, shift left shift right, then I will write here request command in equal to 3, then it will perform this operation. Otherwise request command in equal to 4, then it will perform the operation. We can write as a design engineer according to the specification we need to write. Okay,
Okay, ma'am.
have any doubts? No? Okay. We'll write a simple test bench here using Verilog HDL. So whatever the inputs, all inputs and outputs we have written, and this is the DUT. Here DUT is there, right? This DUT we need to connect. Okay. And next clock we have generated forever clock, and we have dumped the files. Dumpwares dollar monitor, you're displaying dollar monitor here, and see input command in equal to 1. Command in equal to 1 means what? Addition operation. So what data input we have taken? See, this is the data input, and tag 00. Command in equal to 1, data input, tag. Command input equal to 2, command input equal to 5, command input equal to 6. 0 means no operation, 1 means addition, 2 means subtraction, 5 means shift left, 6 means shift right. Okay, request data inputs. After some time we have given this. Okay, changed the inputs. Now we'll say what is the output. So request data input here. For request data input, what is the value? 678. And 4200 request data 1 output data. Six, 7, 8. How we are getting 6, 7, 8 means request data in request data in is 6, 7, 8. Okay, we'll check here only. Output data. We'll write in decimal. Otherwise, you take separate monitors. Okay, I have taken all in single monitor. Take separate for port 1, port 2, port 3, port 4. Then it will be easy for you to check output. Take 0D here. Afterwards, take 0D. What is the input data here? Response 1. Response is correct, getting correctly. Response 1. Tag 0, 1, 2, 3. Okay. Request command in 1. Request command in 1 means what is the request data in? Initially 3054196, right? So what is the value for that output data 1? Check here. 30974,272. Okay, after the delay we getting the output where we have taken the input at this point at fourth line, but output is getting at fifth line. At fifth line, okay, because of delay. Okay, it should get the output value after some delay, right? So check that value whether data input is doing the addition operation or not. What is the data input here? Input 1, input 2. Okay, here request data in is assigning to input 1, request data in is assigned to input 2. Okay, that means same value is assigning both the inputs. Okay, so uh, suppose here I'm taking request in 1 as 305419896. With the same value you need to do the addition operation and check the value. Okay, like that command 4, command 5, 6. Can you connect with the next session quickly with same link?